Hello, this is chapter 16, homework, how to do it video. Okay. So, So this is the original credit card data. When I look at this, I don't see anything really that means anything. So let's look at the segmented data. Okay, there we go. So as you can see, those orange dots kind of go higher. So there's not many of the other dots that are higher. So there could be some, basically this means that the different segments are not scattered randomly. So there might be a different relationship for the different colors. So there we go. Boom. That was easy. Okay, now let's look at this some more. Oh wow. So this is actually the same problem. So if you graph a line through the orange data, it goes up. The blue data goes that way, and everything's going in a different direction. So I would say every single one of them has a different line, so they definitely, it looks like they follow different relationships. So are they justified in worrying that one model might not be able to fit everything? Of course, because one model can't fit things that have different relationships. Okay, so now the predicted sales. These are always the hardest problems for me. Let me try to get a calculator working. Okay, so now, so the predicted sales is the formula. This one right here, sales hat. It equals 7.49 plus 0.982 times the number of salespeople working, which it says is 500. So that would equal 498.49, which rounds off to 0.5. Okay, is that likely to be useful? Well, it's only useful if it's within the range of the data that created the predicted sales formula. So that included businesses that had between 2 to 20 salespeople working. So you cannot use that formula at all for a business that has 500 employees working. That is just a strict rule of statistics. You cannot extrapolate beyond the range of the data. Okay, so is this prediction likely to be useful? No, definitely not. It is, well actually I take that back. You can extrapolate a tiny bit beyond the data that you have, but even that is very dangerous. Sometimes you can't even use the model even within the range of the data. But you definitely cannot extrapolate very far away from the given data. And 500 employees is very far away from just 20 employees. Okay, I almost didn't see that point. See, these points are going that way, but then there's this one point way over there. So if you drew a line through these points, it would start right there and go up that way. But if you drew a line through all the points, including this one, it would start from here and go over through these points that way. So it would be two completely different lines. So if it's away from the average, then it has high leverage. If it's away from the direction of the other points, then it is an outlier. And so it's both, has high leverage and it's an outlier. Okay. Whoops. Sorry. Except the slope would be going up if it goes through these points over here, but if it goes through this point over here, it would be going flat. And so if it goes flat, that would be a reduction in the slope. So it would be, if you had that outlier there, then it would reduce the slope. Oh boy, whenever there's an easy problem, it always makes me worry that the next problem might be really hard. So let's find out. Wait. Oh no, I didn't mean to do that. Okay, well maybe not. Okay, so the first plot looks like a line. I would say a re-expression means doing something like taking the square root or the reciprocal or the logarithm of the data. Anything to make it look more straight. And if it's already straight, you don't need to do that. So I would say no, because the scatter plot already shows a line or a linear pattern. And the residuals are random, like this is just very random. So that's good actually if they're random. And a transformation is not needed. Okay. Uh-oh. That is a very curved line. I mean, a very curved, it's not even a line, it's a curve. So you cannot use regression to do something like that. This actually reminds me, in nuclear physics, there's something called jump, smile, jump. You can look that up sometime if you want to. Okay. So I would say no. It's definitely not linear. Okay. Okay, wow. Okay, this is a good example of one where you can do a transformation to make it a whole lot better. So generally, when it's curved like this, in other words, it's getting close to the y-axis and then curving, and then getting close to the x-axis, that looks kind of like part of a hyperbola. Well, I don't want to use complicated words. It just looks like it's curving between the y-axis and the x-axis. And so a good idea would be to take the reciprocal, because this kind of looks like the graph of 1 over x. And so if you took the reciprocal of that, you just get x, which would be a straight line. Or it also kind of looks like it might be a logarithm. It depends on whether it's getting close. Well, a logarithm has, well, anyway, you would have to maybe try both of them and just find out which one worked better. So you could take the log or the reciprocal of the variable, which is the y variable, the dependent variable, which is cost per unit. Because the other one is just a quantity, like number of units. It wouldn't make sense to take a transformation of that variable. So this is a company that's growing really fast. Growing, then it curves up and grows even more, then it grows even more. That's a lot of good growth for that company. So what if you wanted to get rid of that curve and you tried to just take the reciprocal? Oops, this isn't the right exact kind of curve though, because if you take the reciprocal of it, it just curves down instead of, I mean, it's still curved basically. So it didn't really help. So it's still curved just as much as the original one was. So I would say no, still not straight enough. What's another idea you could do? Well, if something is growing really, really fast, sometimes you have to take the logarithm of the data values. So I'll try that. Squaring them, if you look at those original numbers, squaring them would make it curve up even faster. The negative reciprocal would just flip it upside down. It wouldn't help make it any better. So the only option that remains is the logarithm. Okay. So, before I show a picture, what do you think? Is there any evidence that the age at which women get married has changed over the past 100 years? Well, it'd be interesting to find out. If the graph just kind of stays the same, then probably not. But if we see any type of curve in it, then yes, then something has changed probably. So I don't know what it's going to look like. Let's just find out. Very interesting. Are you ready? Dun dun dun. Wow, this is a huge change. So something crazy happened. Wow, this is crazy. Like right about 1945. What do you think happened around 1945? Or maybe ended in around 1945? Hint, it starts with two W's. The abbreviation for it starts with two W's. World War II. And so the age at marriage was extremely, maybe the youngest ever after that. Then something even crazier happened after that, and it has been going crazy up, like it's never going to stop after that. That is just an extremely steep increase. Something crazy has been going on with our culture. It's totally wild. Okay, so done. There is definitely a pattern, wow. But it's not linear though. I mean, at first it's linear, just kind of sort of slowly going down. And then it actually, after this curve stops, then it's just super linear going up. But then this curve right here is not linear at all. So between about 1940, it stops being linear up until about 1980, I would say. Or maybe something like that. So the trend is linear up to 1940, but then it totally jumps around and curves. Then after about 1975, then it gets linear again. But it's a totally different kind of linear, though. This is fairly regular linear, fairly flat. This is just going super steep. Okay. I would say the association is pretty strong. So I would say as a whole the graph is not linear. There's no straight line that fits all the way from this point all the way to that point and goes through all the other points. So it would have a low correlation because it's non-linear as a whole. So linear model is not appropriate. However, remember, this part is linear and then this other part is linear. So if you broke it into two parts from, like, for example, from 1975 to 2003, it would work. But you could not fit you could not fit a linear model, in other words a line, onto the entire graph of data. Okay, wow, this looks kind of like something is happening. So if you try to make one equation of a line that's summarized in a single number, the amount of health, education, and economics of an entire country. Okay, well, first of all, the purpose of statistics is to try to represent big things in simple ways using a single number. Or maybe just a few single numbers. For example, you could summarize someone's entire career in baseball with one number, like how many home runs did they hit. That took them maybe 20 years to hit all those home runs, but that single number would still represent that entire time. So a statistic is a number that represents a lot of information. But it's probably impossible to represent in one single number the health and the education and the economics of a country. That's just too many dimensions of information to represent with a single number. So if you tried to do it, especially with a line, you'd get a graph that looks kind of crazy. So I mean, this relationship is not straight, and there's probably no way you could ever figure out a good way of doing it. So it would be very misleading if you tried to do a linear model. Okay, so now, if we did fit a line to this data, imagine drawing a big black line across this, from this corner all the way up to that corner. Now, what's the difference between the true value minus the predicted value? Well, it'll be like a big frown, because these predicted values would be underneath the line, because the line would be in the middle. These ones would be above the line. So they'd be curved downward like a frown. And then there's an outlier over there. Wow, that's way away from the center of the data. So that's has high leverage, and if I took away that point, would it help? No, because the data would still be curved anyway. So it wouldn't really help. So would it improve the model a lot? No, it'll still be curved, even if you took out that last outlier. Now I hope you remember what outliers mean technically. An outlier is something, remember in class when we learned about the quartiles, the first quartile Q1 and the third quartile Q3, when we made box plots. If you measure the distance between them and you add 50% onto that distance, then any point that's beyond the top or bottom edge of the box plot by more than 50% of that distance between the beginning and the end of the box, that's classified as an outlier. But usually in pictures you can just tell what an outlier is just because it's way far away from the rest of the data. But there's a technical definition for an outlier though. Okay, so now this is interesting. So this is a fun game to play. And it's hard to get these all completely correct. So imagine that you have 5 data points in kind of like a shape like that. One here, one here, one here, one here, one, and one in the middle. Those points are symmetric in all 4 directions. So that means that there's going to be no correlation between all 5, because this corner, this corner, this corner, this corner, and this corner, they're all pointed equally in all directions, at least in all 4 directions. So left, right, top, and bottom, it's all equal. So what would happen if you added 1 red point onto those 5 points? So in other words, if you added the point A onto it and you do a line through the blue points and point A, then the line would go this direction, right? From this corner down here up through point A. So it would make a positive line, right? I'm estimating it'd probably be 0.75. So 0.75 would be point A. Okay, now how about point E? That would be going downwards, right? Strongly going downwards, and it has a lot of leverage, so probably be fairly big negative number. Now that the correlation, okay, so ready? Wow, this is complicated. Okay, well, let me go with C first. C is still right in the middle, so I would still say the slope would be 0 if you had C in it. So I'll pick, for 0, I'd pick point C. So I've eliminated C and A. And then, what about point B? Point B would probably be positive, because it's a little bit above the midpoint. So I'd say point B would be that one. Then how about point D? I'd say D would be a little bit negative. Fairly negative, actually. So I'd pick point D for there, and then point E, I'd pick that one for the last one. Now, I don't know if I've gotten them right. I'll just have to just guess. So which one could be wrong? Okay, then the ones that might be wrong are D and E. Maybe. It's really hard to tell. Which would be steeper if you graphed through point D or point E? So let me try switching these around. Okay. Wait, if that one's that one, then negative 0.40 would be oh boy. Let's try that. Okay, good. I wish I could draw on the screen. That would have made it easier to figure those out.